Now that we've studied compact and sequentially compact sets, we're ready to tie them together. So the goal of this video is to show this result, which is true for any metric space. A set A is compact if and only if it is sequentially compact. So first let me remind you that we say a set is compact if every open cover of that set yields a finite subcover. On the other hand, we say that a set is sequentially compact if every sequence in that set yields a subsequence which converges to a limit also in the set. So we've studied both of these notions separately, but now we're ready to say that they are actually equivalent for a set. So the goal of this lecture is to prove this statement, and I've animated this on the computer as much as I can because I think it's hard to follow this without good visualizations. So we'll start with the forwards direction, and for that we're actually going to prove the contrapositive. So in order to show that if A is compact, then A is sequentially compact, we will instead prove that if a set is not sequentially compact, then it is not compact. That proof is faster than the backwards direction. For the backwards direction, we will first start with a lemma. And to prove the lemma, we will end up doing a proof by contradiction. The lemma is actually the bulk of the backwards direction, though, so once we've established the lemma that we're going to work through, the rest of the proof is actually a pretty fast direct proof. Once we've established this equivalence between compactness and sequential compactness, we will just kind of recap what these sets tell us, and we'll have a major conclusion which will lead us into our upcoming material. All right, so let's start with the forwards direction. As I mentioned a moment ago, we are going to prove the contrapositive. So suppose the set A that we are looking at is not sequentially compact. What would it look like to negate the idea that every sequence in A yields a subsequence which converges to a limit in A? We have to imagine that there exists a sequence in A with no subsequence converging in A. It's possible that the sequence actually yields a subsequence converging outside of the set, but no subsequence will converge in the set. With that hypothesis, consider the set of sequence points, which I've tried to picture over on the right, although as we'll see in a moment, my image is not perfect. Before we continue our formal write-up, let me ask you a couple of questions. So my first question is, can any term in the sequence appear infinitely many times? Just to give you an example of that with the sequence of real numbers, consider the sequence 0, 1, 0, 2, 0, 3, 0, 4, etc., etc. This is a divergent sequence, but the term 0 appears infinitely many times. Can that happen with our hypothesis? Hopefully you recognize that if I just extracted from that sequence the subsequence of zeros, that would produce a constant sequence which would converge to 0, which must be in the set since it belongs to the sequence. So no term in our starting sequence can appear infinitely many times because that would generate a constant subsequence. So that means that this image I have here over on the right really should have infinitely many distinct points. Some of those points might appear like 8 times in the sequence, but since none of them can appear infinitely many times, we must have infinitely many different sequence terms. So in my set A, imagine infinitely many orange dots. Okay, my next question for you is, can any point in the set of sequence points, so viewing the sequence points as just a set in their own right, can any of them be an accumulation point? To illustrate this question with a sequence of real numbers, consider the sequence that I've given you here. 0, 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, 5, 1/5, 6, 1/6, etc. I wrote it this way so that the sequence would be divergent, but notice that we have these terms, 1, 1/2, 1/3, 1/4, 1/5, 1/6, which if we put them in their own subsequence would be converging to 0, which is actually an element in this sequence and therefore in the set. What I'm trying to illustrate here is that if any of the terms in the sequence are an accumulation point for the set of sequence terms, then you could actually construct a subsequence converging to that accumulation point. And again, that's a point in the sequence, so it's in the set. So the straightforward answer to this question is no. No point in the sequence can be an accumulation point for the set of sequence terms, otherwise there would be a subsequence converging to that point and therefore converging in A. So it's possible that there are accumulation points for the set of sequence terms, but they cannot live in A because we cannot have any subsequence converging in A by assumption. What these two questions are leading us to realize is that when we consider our set of sequence terms, each point appears finitely many times and is isolated with respect to the rest of the sequence terms. So in my picture, you want to imagine infinitely many orange dots and relatively separated from each other. In fact, what we can say is that for each term in the sequence, there's some radius for that term. Here I'm calling it epsilon sub k to go with the kth term. So that when I sketch the neighborhood around the kth term with that radius, it contains no other points from the sequence. Essentially, what we're doing is separating the terms in the sequence with these neighborhoods. We are isolating these terms from each other. Keep in mind what we're trying to do. We are trying to prove that the set A is not compact. That means I want to create an open cover of A which yields no finite subcover, and we are actually on the way to doing that now. These neighborhoods around these sequence terms that we've created are forming the start of an open cover. But as my picture illustrates, it's possible that we are not yet covering all of A. What I would like to do is collect all of these neighborhoods together to form, say, most of the sets in the open cover, and then I want to try to cover everything else with just one more open set. Here's how we're going to do that. The guiding principle is that I want to cover everything outside of these sets. So I kind of want to look at like the complement of all of these open neighborhoods that we've sketched. However, I have to be sure that I cover any terms in A which, say, sit on the boundary of these neighborhoods. So what we're going to do is take each of the radii that we've sketched and cut them in half. So I'm going to retract those radii inwards. Then I'm going to close them off. And for notational purposes, let capital X be the closure of the union of all of these retracted neighborhoods. Because I'm defining X as a closure, X is a closed set. When I compute its complement, that will be an open set, and that's what I'm trying to sketch here with this purple neighborhood. So this purple neighborhood, X complement, is an open set which covers everything in A not covered by these neighborhoods, as well as a little bit in each neighborhood so that we have some overlap. We want to make sure that we're really covering everything in A. Now when I take the family of open sets, which is X complement, together with all of the original neighborhoods around the sequence terms with their original radii, this forms an open cover of A. Unlike in my picture, there are infinitely many of these smaller neighborhoods covering the individual sequence terms. So this open cover has infinitely many sets. However, we will not cover A if we remove any of the open sets designed to cover a sequence term, because each sequence term is only covered by its own neighborhood. So we need all of them, and they are infinitely many. For example, if I removed the one around the labeled point, I'm no longer covering the sequence term X sub k. So trying to reduce our original infinite open cover down to a finite subcover will not cover all of the terms in the sequence, and since those sequence terms live in A, we will fail to cover A. All right, at this point, we've generated an open cover of A which yields no finite subcover, so the set A is not compact. This concludes the proof of the forwards direction via the contrapositive. By showing that if A is not sequentially compact, then A is not compact, we have in fact proven that if A is compact, then A is sequentially compact. Take a moment if you need to work back through this proof, think about why this open cover works, and when you're ready, move on to the other direction. Now we want to show that if A is sequentially compact, then A is compact. We will go ahead and open with the first line of the proof, which is, let some collection of open sets U sub lambda be an open cover of A. Here I'm indexing with this subscript lambda to indicate that I don't know how the collection of open sets looks. Presumably it's infinite, but it could be an uncountable collection. All right, so in my illustration here, we have some set A, and these red dotted pancakes, these open sets, together are forming the open cover of A. A is contained in their union. Ultimately, I want to show that if A is sequentially compact, then A is compact, but to get there, we have to first prove a lemma. So first, we will claim that if A is sequentially compact, then there exists some special positive radius, which I will call epsilon naught, so that for every single point in the set, the neighborhood of radius epsilon naught that you would draw around that point is entirely contained in one of the open sets from the open cover. So imagine that the radius I have over here on the right works for this statement. So it's a special radius which will make this property true. To illustrate what this statement is saying, imagine down in that lower left corner, I identify that point y, and I create its epsilon naught neighborhood. What this claim says is that some special red pancake in my picture, so one member of this open cover, contains that neighborhood, and in my graphic, it looks like this. So this is quite a powerful claim. It's fairly easy for me to imagine sets where this wouldn't be true, but it's always true for a sequentially compact set. So that's what we have to prove first. All right, hoping that you have the idea of what this radius represents relative to our open cover, let's prove this lemma. We're going to prove it by contradiction. So if there is no suitable such radius, then what we can do is construct a sequence in A. We will choose our first point, which I will denote as y sub 1, so that the unit ball around it does not stay inside a single member of the open cover. So there is no one single set from the open cover that contains this unit ball around y1. Before we move on, let me explain why this must be possible. If I couldn't find such a point y1, then what we would be saying is that for every single point in A, the unit ball around it stays entirely inside of a single member of the open cover, which would mean that epsilon naught equals 1 works for the statement. So if we're assuming that no such radius exists, then for any positive number epsilon that you choose, you can find such a point for which that epsilon neighborhood is not solely contained inside of a single member from the open cover. So when epsilon equals 1, grab y1. When epsilon equals 1/2, go pick a point for that radius, call it y2. When epsilon equals 1/3, find a point for that radius, call it y3, etc., etc. So the jth member in the sequence that we are forming is a point from the set for which the radius 1/j neighborhood around it does not live entirely inside of one member of the open cover. This is something that we can do if we assume that our claim is not correct. To continue with our contradiction, since this sequence lives in A and A is sequentially compact, there must be a subsequence of the original sequence which converges to a point in A. We will call that limit y0. Okay, I want to say a few more things before I kind of pause and put up an illustration of what's happening. Since the limit y0 belongs to the set A, it is contained inside of some open set from the open cover. So identify, say, u sub lambda naught as a member of the open cover which contains this limit y0. One more thing to say before we look at an illustration of what we've set up here. Since that member of the open set, you can think of it as like one of those red pancakes, is an open set, pick delta greater than 0 so that the delta neighborhood we draw around y0 stays inside of u lambda naught. That's just relying on the fact that u lambda naught is an open set so that y0 is an interior point. Okay, let's pause and illustrate what we're doing. I think I will give myself more room, but I'll keep enough so that we remember how the sequence was constructed. Here's our set A, and imagine that I'm graphing the subsequence which is converging to this point y0. Y0 lives entirely inside of u lambda naught. So this is a member of the open cover which contains the point y0. Let's say a little bit about these subsequence terms which are converging to y0. They were chosen to partner up each one with a radius. So around each one, I want to imagine a radius defining a neighborhood which is not entirely contained inside of a single member of the open cover. Now, the illustration I've put up doesn't support our claim that these neighborhoods are not entirely contained inside of any of the u sub lambda by themselves, because the last few points, the ones getting close to the limit, are entirely contained inside of u lambda naught, but that's exactly what we're going to do with our proof. So that behavior that we see close to y naught is what our proof is going to verify happens. The radii I've drawn defining neighborhoods around each of the subsequence points are not necessarily drawn to scale, but the idea is that the jth term in the original sequence has radius 1 over j. So as we go out in our sequence, or as in this picture, as we go out in our subsequence, the radii are shrinking. That's why I've drawn them going from large to quite small. Okay, how are we going to continue with this proof? Well, the last thing I wrote down was imagine that we choose some delta greater than 0 so that the delta neighborhood around the limit is entirely contained inside of the open neighborhood u sub lambda naught. That's what I've just added to this picture. What our proof will ultimately do is demonstrate that those last few subsequence terms I drew in my sketch are accurately drawn, meaning that they are going to land inside of the delta neighborhood, which places them in the open set u sub lambda naught. The reason why we're going to do that is because I have an algebraic description of this delta neighborhood. It's all of the points from the metric space whose distance to y naught is less than delta. Whereas u sub lambda naught, I have no idea what it looks like. So we're going to move from a general open set, which we can't really describe, to something which we have a very concrete description for. Okay, so what is the strategy to show that those points and their neighborhoods close to y naught do land inside of this delta neighborhood? Well, let me give you some technical details and then I'll explain what they're doing. First thing we're going to do is pick a threshold n sub 1, so that for all subsequence indices beyond that threshold, the corresponding terms from the subsequence actually land in the delta over 2 neighborhood around y naught, so a neighborhood which is half the size of what we're currently looking at. And then we are going to pick a second threshold n sub 2 so that n sub 2 is greater than 2 over delta. Or in other words, the reciprocal 1 over n2 is less than delta over 2. All right, let me shrink my delta neighborhood to the delta over 2 neighborhood. So we're going to retract our radius by a factor of 1/2. I am writing these two thresholds down separately and calling them n1 and n2 because each is serving a different purpose. Let me explain what that purpose is now if you don't see it. My condition on n1 is related to the convergence of our subsequence to the limit y naught. So I'm choosing n1 large enough so that my subsequence terms are really close to the limit. That's the goal with n1. Whereas the second threshold, n2, has been chosen to shrink the neighborhoods we draw around them to something quite small, delta over 2 or smaller. So our first threshold drives the subsequence to the limit, and the second threshold is shrinking the neighborhoods that we associate to each term in the subsequence. So it's like get close to the limit and create small neighborhoods. That's ultimately going to put us inside of u lambda naught. We want to see both of these behaviors. We want to be close to the limit with small reciprocal neighborhoods. So let n be the maximum of these two thresholds and just identify some subsequence term, which I will call y sub nj, whose index is beyond this threshold and therefore beyond the two individual thresholds n1 and n2. In my picture, you can imagine the term I'm pointing at is such a y sub nj. It is within distance delta over 2 of the limit y naught, and the radius defining a neighborhood around it is also very small. It's less than delta over 2. So this is a good choice of a term to analyze. All right, because we're now working with a term very close to the limit and with a very small neighborhood around it, let's zoom in. I want to claim that the neighborhood of radius 1 over nj around this point y sub nj is ultimately inside of the delta neighborhood around the limit. In my picture, it's actually within the delta over 2 neighborhood, but that's stronger than we need. So if I want to show one neighborhood is inside of another neighborhood, that's an example of set containment. So let's identify a point, call it z, from the neighborhood around y sub nj of radius 1 over nj. So here you can imagine z on our picture. How close is z to y naught? By the triangle inequality, the distance from z to y naught is less than or equal to the distance from z to the subsequence term y sub nj, plus the distance from that subsequence term to the limit. Both of these distances we understand. Z is in a neighborhood of radius 1 over nj around y sub nj, whereas the term y sub nj is in the delta over 2 neighborhood around the limit. So both of those distances are bounded above by two radii, 1 over nj and delta over 2. But nj is greater than or equal to n, which is greater than or equal to n2. So 1 over nj is less than or equal to 1 over n, which is less than or equal to 1 over n sub 2. So by replacing the denominator n sub j with the second threshold, we go up in size. But we chose that second threshold n sub 2 so that 1 over n sub 2 is less than delta over 2. So overall, the distance from z to y naught is less than delta. However, if you think back to how we created our subsequence, for epsilon equals 1 over nj, we selected y sub nj so that the 1 sub nj neighborhood around y sub nj was not solely contained by a single member from the open cover. Yet now we've shown that if A is sequentially compact, you actually cannot do that. Because here, the 1 over nj neighborhood around y sub nj is entirely contained inside of the delta neighborhood around the limit, which we know to be entirely contained inside of the open set u sub lambda naught from the open cover. So that violates how the sequence was constructed, which means the construction wasn't possible. Therefore, there is such a special radius epsilon naught. Okay, that concludes the lemma. So the lemma was that if A is sequentially compact, then there is a special radius epsilon naught greater than 0, so that the epsilon naught neighborhood you draw around any point in the set lives inside of a single member from the open cover. That now gives us the second sentence in our proof. So to recap, we want to show that if A is sequentially compact, then A is compact. It's going to be a direct proof. What we can now say is that given some random open cover of A, we can identify a special radius epsilon naught greater than 0, so that for each point in the set A, the neighborhood around that point of radius epsilon naught is entirely contained inside of a single member from the open cover. Let's move on now and finish the proof. Thinking back to our discussion of sequentially compact sets when we first learned them, we proved that if A is sequentially compact, then A is totally bounded. Therefore, for this special choice of radius, there exists a finite set of points in A, so that A is covered by their epsilon naught neighborhoods. So here I'm just imagining A as covered by a bunch of symmetric little neighborhoods, and what's important is that there are only finitely many. Using the lemma that we just proved, for each member of this collection of epsilon naught neighborhoods, there exists a member from the open cover which contains it. So for each index k, where k runs through the finite set from 1 to capital N, identify a u sub lambda k from the open cover so that the epsilon naught neighborhood around xk from that finite set of points is entirely contained inside of u lambda k. If you're a little lost at this point, after the proof, I will illustrate this with more graphics. But before we do that, let's wrap up. We're almost done. Now we can say that A is contained inside of those epsilon naught neighborhoods. There are capital N of them. However, from the lemma, that family of epsilon naught neighborhoods is contained inside of a family of capital N neighborhoods from the original cover. Therefore, A is covered by capital N members from the original open cover, which means that that collection of capital N neighborhoods is a finite subcover of A. So given this random open cover that we started with, we were able to reduce it down to a finite subcover, so A is compact. All right, we are done with that proof, but I think it's very easy not to picture exactly what's going on in the middle here, so let me give you an illustration. Imagine this is our set A, and we've dropped some open cover on it. By the lemma, assume that this radius works meaning that if I take any point in the set and draw a neighborhood around it of radius epsilon naught, it's entirely covered by one of these red dotted members of our open cover. So it's covered by a single pancake. However, we also know that A is totally bounded, which means that for this radius, I can go find a finite collection of points so that when I take those points and create their epsilon naught neighborhoods, that collection of neighborhoods covers A. So in this graphic, we've kind of forgotten about the open cover. It's like from the open cover, we define the radius, and then with that radius, I find a finite collection of points so that A is covered by these symmetric yellow neighborhoods. But now this family of neighborhoods is what we will use to generate a finite subcover relative to our original cover. And here's how we do it. For this neighborhood, by the lemma, we know that it's entirely contained inside of a single member from the open cover. So for that neighborhood, pick this member of the open cover. Move on to the next. For this neighborhood, go find an open set from the cover which covers that neighborhood. Move on to the next. For this neighborhood, there's some open set from the original cover containing that neighborhood. I'm not going to keep doing this, but this is the idea. For each of these yellow neighborhoods, we go back to the original cover and grab some pancake from the open cover which contains that neighborhood. If I have, say, 30 of these yellow neighborhoods, I will end up identifying 30 red neighborhoods, and those form the finite subcover of A. Okay, I hope this illustration helped you understand this direction of the proof. At this point, we are actually done. We have proven that A is compact if and only if A is sequentially compact. So to recap, if A has the property that every open cover of A yields a finite subcover, that is equivalent to saying that every sequence in A yields a subsequence which converges to a limit in A. When we learned each of these topics separately, we had some implications, and let's review them. We said that if A is sequentially compact, then A is totally bounded. In fact, we used that in the proof. And when we discussed total boundedness, we proved that a set which is totally bounded is just plain old bounded. On the other hand, when we defined compact sets, we said that if A is compact, then A is closed. So now, reading kind of up and down on this chart, we arrive at a major conclusion, which is that if A is compact, then A is closed and bounded. The backwards direction is not true. We've seen examples, actually. So any infinite set in a discrete metric space is closed and bounded, but it's not compact. However, in our next lesson, we are going to talk about Heine-Borel, which says that in Euclidean space, compact is equivalent to closed and bounded. We know that the forwards direction is always true. In every metric space, if a set is compact, then it is closed and bounded, which means that all we need to show for Euclidean space is that if a set is closed and bounded, then it is compact. If you're wondering if there is an if and only if statement for general metric spaces, yes, you just have to strengthen both closed and bounded. So in general, a set is compact if and only if it is complete and totally bounded. That's not too hard to connect to Heine-Borel for Rn. Any closed subset of Rn is complete. We actually proved that a closed subset of a complete space is complete in its own right. And also, bounded and totally bounded mean the same thing in Rn. So really, this is like a generalized form of Heine-Borel for general metric spaces. Okay, so that's what's coming up next. I hope you enjoyed this look at the equivalence of compactness and sequential compactness. Thank you for your attention.